Right now, beneath the surface of the Chicago Sanitary and Ship Canal, the U.S. Army Corps of Engineers, USACE, is operating one of the most energy-intensive biodefense systems in the world. It is an electronic dispersal barrier, a massive piece of infrastructure that consumes between $11 and $16 million in electricity annually. The total capital investment to construct this system has already exceeded $200 million. The sole objective of this massive expenditure is to stop the migration of Asian carp, specifically silver and bighead carp, from the Mississippi River Basin into the Great Lakes. This situation presents a staggering economic paradox. In China, these specific species are critical agricultural commodities, serving as a primary protein source for millions. Yet, in the United States, the exact same biological organisms are classified as a Tier 1 environmental threat. The government is not harvesting them. It is spending a fortune to repel them. This raises a critical question for any pragmatic observer. Why is the United States deploying military-grade infrastructure to electrocute a biomass that other nations consider a food resource? Why choose a solution with zero return on investment instead of industrial commercialization? Furthermore, we must address the engineering validity of the solution itself. The system relies on pumping high-voltage direct current into a conductive fluid medium. Basic physics suggests that maintaining a precise voltage gradient in moving, conductive water is inherently inefficient. So, does this $200 million invisible wall actually work, or have the carp already found a physical loophole to bypass the current? To understand why the U.S. Army Corps of Engineers committed to a multi-million-dollar electrical infrastructure project, we must first analyze the technical specifications of the adversary. The Asian carp, specifically the bighead and silver carp varieties, are not standard aquatic wildlife. They function as high-efficiency biomass processing units that systematically dismantle freshwater ecosystems. Biologically, these species possess a metabolic rate that demands a daily intake of plankton equivalent to 20 to 40% of their total body weight. In a nutrient-rich environment like the Mississippi Basin, a single 40-kilogram fish consumes up to 16 kilograms of biomass every 24 hours. Their feeding mechanism utilizes specialized gill rakers to filter zooplankton and phytoplankton directly from the water column. This process effectively removes the foundational food source for native species. Larval sport fish, such as walleye and yellow perch, rely on this same plankton to survive. The data from the Illinois River is alarming, where invasive carp now constitute up to 90% of the total aquatic biomass in certain stretches. They have not just competed with native species, they have statistically erased them. The reproductive output is equally industrial in scale. A single mature female Asian carp can release over 1 million eggs annually. The growth rate of the offspring is rapid, allowing them to outgrow the mouth size of most native predators within a single season. This reproductive velocity renders traditional population control methods mathematically impossible. Beyond the ecological displacement, the silver carp presents a direct kinetic hazard to human activity. This species possesses a unique physiological reaction to the acoustic frequencies generated by outboard motors. When startled by hull vibration, they leap vertically up to 3 meters, or roughly 10 feet, out of the water. These are not small animals. Mature adults weigh between 10 to 20 kilograms. A rigid 20-kilogram object striking a boat pilot traveling at 30 miles per hour generates an impact force comparable to being struck by a bowling ball dropped from a second-story window. There are documented cases of broken jaws, fractured ribs, and damaged navigation equipment. This behavior transforms a commercial shipping channel into a combat zone, threatening the safety of crews operating heavy industrial barges and decimating the recreational boating industry in infested regions. Prior to the construction of the electrical system, both state agencies and private citizens attempted to curb the population through conventional means. Commercial harvesting programs and physical netting operations were deployed, but the biomass was expanding faster than it could be physically removed. The economic devastation in the Mississippi Basin served as a warning. If these fish breached the system, they would threaten the Great Lakes fishery, an asset valued at over $7 billion annually. The government concluded that population reduction was not a viable strategy. Absolute exclusion was the only remaining option. This decision shifted the focus to the geography of the conflict, specifically the Chicago Sanitary and Ship Canal. This canal is the critical hydrological link. It is a 28-mile artificial waterway engineered in 1900 to permanently reverse the flow of the Chicago River, connecting the Great Lakes Basin to the Mississippi River Basin. It is the only aquatic pathway for the carp to exit the river system and enter Lake Michigan. However, simply blocking the canal with a concrete dam was impossible because it serves as a vital artery managing over 1.2 billion gallons of treated wastewater daily and carries 15 million tons of commercial cargo annually, an economic flow valued at nearly $16 billion. Recognizing this choke point, the Army Corps initiated the construction of the Electric Dispersal Barrier project in 2002 at River Mile 296. The engineering challenge was significant. Crews had to install massive 4-inch thick steel electrodes into the bedrock of the canal floor and construct high-capacity power stations on the banks. This process required years of excavation and electrical calibration to create a field strong enough to stop a fish, yet stable enough to allow steel ships to pass, setting the stage for the activation of the high-voltage field. To understand how a system without a physical net stops millions of tons of biomass, we must analyze the hardware architecture and electrical principles of this project. It is not a simple fence. It is a complex industrial array designed to maintain a precise energy field within a chaotic fluid medium. The core infrastructure lies entirely beneath the water surface. Anchored into the limestone bedrock of the canal floor are massive steel electrodes. These steel billets, some weighing over 2,000 pounds each, span the full 160-foot width of the channel. They are connected via shielded underground cables to the control buildings on the bank. Inside these structures, high-capacity pulse generators convert standard utility AC power into a specific weaponized form of energy known as pulse direct current. The engineering decision to use direct current rather than alternating current was critical. While AC current induces immediate paralysis, it is statistically lethal to humans and accelerates galvanic corrosion on steel ship hulls. If AC were used, the propellers of passing barges would corrode and fail within months. DC current, however, allows engineers to manipulate fish behavior through specific neurological responses without destroying commercial infrastructure. The system operates by pulsing energy into the water column to create a voltage gradient, specifically calibrated to 2.3 volts per inch. To the average person, 2.3 volts sounds harmless, less than a standard battery. But this is a misleading metric. In fluid dynamics, voltage stacks over distance. For a small 2-inch minnow, the shock is negligible at only 4.6 volts total. But for a massive 1-meter Asian carp, the body acts as a 40-inch conductor. The potential difference between its head and tail hits nearly 92 volts. To put this in a human perspective, if a 6-foot-tall human fell into this water, their body spans 72 inches. That equates to 165.6 volts surging through the central nervous system instantly. This is significantly higher than a standard US wall outlet, but delivered through water, which lowers the skin's natural resistance to near zero. You would not burn or char like a lightning strike victim. Instead, your diaphragm would instantly lock tight. You would die from asphyxiation because you physically could not force your lungs to take a breath. This same physics applies to the carp. The current intercepts the central nervous system of the fish through a strictly defined 3-stage escalation process. The process begins at the periphery of the barrier, known as the wide array. As the fish enters this zone, it encounters a low-frequency pulse of approximately 5 to 10 hertz. This creates a sensation of physical distress, similar to a mild but constant muscle cramp. The engineering goal here is behavioral modification, creating a zone of discomfort that convinces 90% of fish to turn back voluntarily before the pain escalates. If the fish ignores the warning and pushes into the field, it enters the phenomenon of Galvanotaxis. This is where engineering overrides biology. As the field strength increases, the DC current hijacks the motor neurons. The fish loses voluntary muscle control. The electricity forces the muscles to contract in a specific rhythm, involuntarily steering the fish toward the positive electrode. The fish is no longer an independent organism. It is a biological drone being remotely piloted by the shore station. The final failsafe, known as tetany, occurs if the fish breaches the center of the trap where the gradient hits the full 2.3 volts per inch at frequencies exceeding 30 Hz. At this level, neurological stimulation peaks. Every muscle in the body of the fish, including the heart and gill arches, locks into a rigid and sustained contraction. Respiration ceases. The fish becomes a stiff and floating object that cannot swim or breathe. At this point, the natural hydraulic flow of the canal, moving at roughly 1.5 to 2 feet per second, takes over and sweeps the paralyzed biomass back downstream. Once the fish drifts out of the charged zone, it typically recovers muscle function within 5 to 10 minutes, but the migration attempt has been mechanically terminated. The most significant operational challenge is the specific conductivity of the water. Canal water is not a stable wire. Its ability to carry current changes based on temperature and dissolved solids. In winter, cold water becomes more resistive, forcing the generators to output massive voltage just to push the current through. In summer, or after an industrial runoff event, conductivity spikes. The water becomes too efficient, risking an overload that could blow the multimillion-dollar pulse generators. To counter this, the system employs real-time monitoring algorithms that adjust power output every millisecond, ensuring the field remains impenetrable whether the water is freezing or boiling. The immediate question surrounding this $200 million investment is whether it has actually succeeded. When analyzing the operational data from the last decade, the return on investment manifests in two distinct categories: biological containment and economic preservation. From a biological standpoint, the system has achieved its primary directive. Since the activation of the high-voltage barriers IA and IIB, the leading edge of the adult Asian carp population has remained statistically stalled roughly 47 miles downstream from Lake Michigan. Extensive monitoring, which includes environmental DNA testing and electrofishing surveys, indicates that established breeding populations have not successfully breached the electrical gauntlet. The barrier has effectively frozen the migration front in place. This containment protects the Great Lakes ecosystem, which hosts native species like walleye and lake trout that would otherwise face immediate starvation due to plankton depletion. However, the financial metrics provide the most compelling justification for the continued energy expenditure. The Great Lakes fishery is an asset valued at over $7 billion annually. This industry supports more than 75,000 jobs across the region. When calculated against this figure, the $11 to $16 million annual operating cost of the barrier represents an insurance premium of approximately 0.2% of the protected asset value. In purely economic terms, spending millions to electrify the water is vastly cheaper than the total collapse of a multi-state fishing economy. Beyond the fishery, the engineering design of the barrier secured a critical logistical victory. The Chicago Sanitary and Ship Canal is not merely a drainage ditch. It is a heavy industrial artery moving over 15 million tons of commodities every year, including petroleum, coal, and road salt. A physical solution, such as a concrete dam, would have permanently severed this supply chain, forcing cargo onto trucks and rail, which would have increased transportation costs by hundreds of millions of dollars annually. The electric barrier achieved a unique dual-state outcome. It functions as a solid wall for biological organisms while remaining completely permeable for commercial steel tonnage. This project has also generated an unprecedented dataset regarding aquatic behavior under electrical stress. The Army Corps of Engineers has inadvertently created the world's largest laboratory for study on Galvanotaxis. The data collected here regarding pulse frequency, voltage gradients, and fish physiology is now being exported to other regions facing invasive species, proving that direct current can be weaponized as a precise ecological management tool. Yet, despite these successes, the system is not without critical physical vulnerabilities that threaten to undermine the entire operation. Despite the operational success of the electric barrier, the system faces a persistent logic problem often raised by the public. Why not simply harvest the biomass? If China consumes millions of tons of carp, commercial fishing seems like the pragmatic solution. However, the anatomy of the fish renders this economically impossible in the United States. Asian carp possess a complex network of intramuscular bones. Unlike the spine of a trout, which is easily removed, these Y-shaped bones are embedded deep within the muscle tissue. American processing plants lack the automated machinery to remove them, and manual deboning is too labor-intensive to be profitable. Furthermore, the logistics of cold chain transport render exportation unviable. Shipping frozen, low-value protein back to China costs more than the market price of the commodity itself. The invasive population is essentially a biological waste product with a negative commercial value. Recognizing that harvest is impossible and electricity alone has physical loopholes like wake riding, the U.S. government has escalated the conflict. They have approved the Brandon Road Interbasin project with a staggering budget of $1.14 billion. This initiative moves beyond the single barrier concept to create a multi-layered engineering gauntlet at the Brandon Road Lock and Dam, a strategic choke point located downstream from the current barriers. The new design integrates multiple deterrent technologies to ensure zero redundancy. Before a fish can even reach the electric field, it must pass through a complex array of acoustic deterrents. These underwater speakers blast specific frequencies that cause physical pain to the hearing of the carp, driving them back. Simultaneously, an air bubble curtain will be deployed across the channel. This wall of high-pressure air disrupts the water column, confusing the lateral line sensors of the fish and masking the acoustic signature of boat engines that typically attracts them. Perhaps the most critical mechanical upgrade is the engineered flushing lock. In the current system, fish can theoretically float into a lock chamber alongside a boat. The new design utilizes hydraulic pumps to flush water out of the lock chamber and back downstream before a vessel enters, physically ejecting any biological matter from the transit zone. It is a system designed to strip the water of life before allowing commerce to pass. This brings us to the final debate. We are looking at a future where over $1 billion of taxpayer money is spent to stop a fish that we cannot eat and cannot kill fast enough. Do you believe this multi-layered engineering approach is the only way to save the Great Lakes? Or is it an endless money pit fighting a force of nature that will eventually win? Leave your analysis in the comments below. If you found this technical deep dive valuable, please hit the like button and subscribe to the channel for more stories on extreme industrial engineering. Thank you for watching and see you in the next video.